Okay, we can go ahead and get started. So today, what I'm going to go through is just that second PowerPoint in section 4. And that's mostly just the nucleophilic acyl substitutions. So the Fischer esterification, substitution, the acyl chloride reactions, as well as reduction of amides and carbonyl compounds with carbon nucleophiles. So the basics of nucleophilic acyl substitution. So we know in carbonyl compounds, your carbonyl carbon is electrophilic because it's connected to that electronegative oxygen. We're just going to pull electron density towards itself, which makes the carbon partially positively charged and the oxygen partially negatively charged. So carbonyl compounds are electrophilic because of that carbon. If the carbonyl compound has a good leaving group, we can have a substitution reaction instead of what we learned in the past, or what I talked about in the past study session where we have nucleophilic addition. Okay, so if something can come off, you'll have a substitution reaction. And the nucleophile, whatever nucleophile we use, will replace the leaving group. So conversions of less stable carbonyl compounds to more stable carbonyl compounds are spontaneous, meaning you don't have to do any work to get them to occur. They'll occur just without you doing anything, without any work, because you're going from less stable to more stable, which is favorable. More stable to less stable conversions will require work, so heating or doing something to make the reaction irreversible. So here's the basic general mechanism for this. We have our carbonyl compound, our acyl derivative. So we want a good leaving group here so we can have a substitution reaction. And then we'll have a nucleophile. Since this carbon is electrophilic, this nucleophile will attack the carbon, break the pi bond, break the carbon-oxygen double bond. Those bonding electrons will stay on that oxygen and create an oxygen anion, and then we'll connect that carbon in the nucleophile here. So then, because this is a substitution reaction, so remember substitution, we have addition and then elimination. So we have our addition step here where we're adding our nucleophile to the carbon, and then we'll have our elimination step where this leaving group will come off. Okay, and at the same time, a lone pair of electrons from oxygen will come down and reform the double bond, and that leaving group will come off. So you'll end up with a substituted carbonyl compound, where you just substituted the nucleophile for whatever leaving group you had here. Okay, so this is from the PowerPoint I just put in here to reference. So this is showing you what, these are all acyl derivatives. It'll show you what acyl derivatives are more stable, less stable. So when we have interconversions, which means going from one acyl derivative to another acyl derivative, if we're going in this direction, then it'll be spontaneous because we're going from less stable to more stable. If we're going in the backwards direction, then it'll require work. So we'll have to do something to make that reaction happen. Okay, and these are less stable because this X or whatever is on this carbonyl group is a good leaving group. And the electrophilicity of the carbonyl carbon is not constant for all carbonyl compounds. It depends on what that carbonyl carbon is connected to. So what depends on the reactivity of the carbonyl compound is the electrophilicity. Okay, so down here on this end of the line, the electrophilicity of the carbonyl carbon is higher than on this side of the line, where it's lower. And then also on this side, we don't have a good leaving group, so that also decreases the reactivity. So like in this case, this oxygen anion, we'd have to put in a tremendous amount of energy to break this carbon-oxygen bond. Okay, that's pretty much impossible to do. So this is really not a good leaving group, okay, which decreases its reactivity. But down on this end, halides we know are good leaving groups. So this can come off and react more easily than things on this side of the line. So I'll come back and reference that throughout the rest of these examples. So starting with acyl chloride, which is on this complete and the least stable out of all of these, and the most reactive. So we know to make an acyl chloride into anything else will be spontaneous because it can't get any less stable, at least out of these examples. So we have an acyl chloride with water, which will give us a carboxylic acid. Okay, so we replaced chloro group with this hydroxyl group. Okay, so we're going down the line here, so it is spontaneous. We're going from less stable to more stable. So to do that, if I want to put an OH group here, the nucleophile I would use is something with an OH group, right? So I would use water. Okay, and here's the mechanism for that. Again, I said this last study session, but I would really caution you to, when you're going through these mechanisms and learning these mechanisms, to really try to actually understand why you're doing all of these steps and why electrons are moving, why is something coming off, why is something getting put on, instead of just trying to memorize the mechanism and then throw it back up on a test. So that will really help you in the long run to be able to apply these mechanisms to more compounds, and it won't trip you up as much if you actually understand the specific steps of the mechanism instead of just memorizing it. So I would just recommend you try your best to keep that in mind as you go through and practice these mechanisms. So this oxygen here has 2 lone pairs of electrons, right? It's nucleophilic. This carbon is electrophilic. So this nucleophile will attack this carbon here, which will break this double bond, and these pi electrons will stay on that oxygen up here. Okay, so we added this whole thing here, made a carbon-oxygen bond, okay, and then we formed an oxygen anion up here. So if this oxygen down here has one too many hydrogens and a positive charge, and this oxygen up here has not enough hydrogens, it has a negative charge, what do we think is going to happen is we're going to have an intermolecular proton transfer, right? Because if one oxygen in the molecule has too many and one has not enough, it's logical that you would move a hydrogen from the one that has too many to the one that doesn't have enough. So that's what we do here. We have an intermolecular proton transfer. Move this hydrogen up to this oxygen here, and then we get this intermediate. So now we got rid of our charges here. Okay, but this chloro group is still a good leaving group, right? So this chloro group will come off, and at the same time, if it came off, okay, we would just form a positive charge on that carbon, okay? But that can't happen. We don't want that. Okay, so to prohibit that from happening, these lone pairs of electrons from this oxygen will come down and form a double bond to keep this carbon tetravalent. Okay, so chloro group will come off, and the lone pairs of electrons on oxygen will come down, form a double bond. Okay, and I just moved this OH group up here. Okay, so that's how we get here. But now this oxygen has one too many bonds. We have a positive charge again. Okay, but we know that hydrogen will come off no problem spontaneously. We don't have to do anything. Okay, so this hydrogen will come off, combine with the chlorine, make hydrochloride or hydrogen chloride, and then our product here is carboxylic acid.
Which had too many bonds?
This oxygen up here. We have 3 bonds, oxygen wants 2, so it has a positive charge. But we'll take off that hydrogen, make hydrogen chloride and carboxylic acid. Okay, following me? Okay, so similarly, if we react an acyl chloride with an alcohol, okay, instead of a carboxylic acid, we can make an ester. Okay, so the mechanism is very similar. This oxygen here is 2 lone pairs of electrons. It's nucleophilic. This carbon is electrophilic. Okay, so the lone pairs of electrons will attack that carbon, break the double bond, and those pi electrons will stay on this oxygen up here. So we'll have an oxygen anion, okay, and this oxygen has too many bonds, has a positive charge, okay. So same thing's going to happen where this oxygen has too many bonds, this one has not enough. This hydrogen will move from here on this oxygen to this one up here. So we'll have another intermolecular proton transfer. Okay, so that's how we get here. We took this hydrogen from this oxygen up here.
I
Hello.
was just in there before my backpack.
Yeah, I was wondering if that was.
Sorry about that.
No, you're okay.
Thank you.
Anyway. Okay, so we got here. Okay, but same thing from here. This chlorine is still a good leaving group, so that's going to come off. And to keep that carbon tetravalent, these lone pairs of electrons will come down, form a double bond. Okay, so and we'll end up here just like we did here, except this now we have an R group here instead of an H. But now that oxygen again has too many bonds, but this hydrogen will come off no problem, combine with the chlorine, have hydrogen chloride, and then an ester. Okay. So these are interconversion reactions where you're going from one acyl derivative to another acyl derivative. Easy enough, right? Okay. So another example of this is of interconversion. It's Fischer esterification. Okay. So Fischer esterification, we have a carboxylic acid and an alcohol. Okay. It's acid catalyzed, and we end up with an ester. Okay. So we go back here and look at our chart here. Here's a carboxylic acid, and here's an ester. So we're going backwards. Okay. So that's going to require us to do something to make that reaction more favorable, to make that reaction irreversible. So if you remember in class, we was talking about when we did this in the lab, we used that side arm to catch the water. Okay. And if we remember Chatelier's principle, which says that if you remove a product from a reaction, it'll shift the reaction towards the products to make more. Okay, so water is a product of this reaction. If we remove the water as this is occurring, it's going to shift this equilibrium towards the products, making it irreversible. Okay, so even though we're going backwards in the line of stability, this can still occur. We just have to do some more things. And we also have to catalyze with acid as well. So here's the general mechanism for that as well. So this one's a little bit different. So we see here the electrophilicity of this one is lower, okay, than over here. This electrophilicity of this carbon is higher, so we didn't have to do the protonation thing where we make a strong electrophile, because this was already a strong enough electrophile. But this one is down near this side of the line, so this electrophilicity isn't strong enough to combine with an alcohol just yet. So we'll have to do the protonation thing that we're familiar with, or we should be familiar with by now. So that's why we catalyze with acid, is because we're going to protonate this carbonyl oxygen up here. Okay, and this is hydronium H3O+, which we get by dissolving strong acid in water. So we protonate this oxygen up here, okay, which gives this oxygen a positive charge. It'll pull those pi electrons towards itself, which will enhance the partial positive charge on this carbon, okay, which makes this a stronger electrophile. Okay. So now that this is a strong electron, now we can react with the alcohol, which is a weak nucleophile. So again, oxygen has 2 lone pairs of electrons. It's a nucleophile, so it'll attack the electrophilic carbon here, okay, which will break this double bond, and those pi electrons will neutralize that positive charge on that oxygen here. Okay. So now that we get here, This right here, that's not a good leaving group, okay? Because we just put that on, why would we take it right back off? But if we protonate this, that would be a good leaving group, right? So again, what's going to happen is we're going to have the intermolecular proton transfer, where we move this hydrogen from this oxygen that has too many bonds up to this oxygen, okay? Or this one, it's arbitrary. So when we protonate this oxygen up here, we end up with water, right? And we know water is a good leaving group. So pretty much anytime you'll see this OH2 with positive charge, you know it's going to come off, because that's a very good leaving group. So after the intermolecular proton transfer, we end up with this. Our water will come off, so that bond will break, okay? And to prevent or to keep this carbon tetravalent, these lone pair of electrons from this oxygen will go to make a double bond, okay? So we end up with this, and again, this oxygen has too many bonds, but that hydrogen will come off, no problem, and we'll end up with an ester here, okay? Everyone following me? Okay. So you have saponification, which is when we react an ester with hydroxide to make a carboxylate. So let's look back here. We have an ester, and we're going to carboxylate, okay? So this is favorable. This is fine because we're going from less stable to more stable, okay? So that will be spontaneous. Okay, so here's our ester here. This is strong nucleophile, okay? We don't have to worry about the electrophilicity of this because it's a strong nucleophile. So lone pair of electrons on oxygen will attack this carbon, electrophilic carbon, break the double bond here, okay, which will make an oxygen anion there, okay, and add this OH here, okay? So if we remember, OR is a good leaving group, right? So OR will come off, and then lone pair of electrons from the oxygen anion will come down to reform the double bond here, okay? And that will make a carboxylic acid, okay? But because we took off this OR here, that will react further with the carboxylic acid, okay, and take this hydrogen, okay, because this is basic. It'll take that hydrogen, which will break this OH bond. Those bonding electrons will stay on the oxygen and make a carboxylate, okay, which is just carbonyl compound with an oxygen with negative charge here, and then an alcohol. Okay, so this is similar to the backwards of Fischer esterification, okay? So in Fischer esterification, we have a carboxylic acid and alcohol, we make an ester. Here we have an ester hydroxide, we make a carboxylate and alcohol. So it's similar, but we're just missing one more hydrogen. Okay, and this is how we make soap, if you remember that whole spiel. Okay, so I have an example here. Okay, so this is an acyl chloride, right? And we're going to add water. Okay, and acyl chlorides are all the way on the left of the stability line. So this is already strong enough nucleophile or strong enough electrophile that it can react with water. Okay, oxygen has 2 lone pairs of electrons. I'll attack the electrophilic carbon here, break the double bond, and those pi electrons will stay on that oxygen up there. No. Okay. Okay. And again, this oxygen down here now has too many hydrogens. This one up here now doesn't have enough. So logically, that would make sense that it would switch, right? So we'll have that intermolecular proton transfer. and switch one of those hydrogens from down there to the top oxygen. Okay. That chloro group is still a good leaving group. So that'll come off. And those lone pairs of electrons on that oxygen will come down to reform a double bond, make that carbon tetravalent. Okay, but now that oxygen up there has a positive charge, we don't want that hydrogen there. So that'll come off, no problem. Combine with the chlorine that we lost here, and then we'll form our product, carboxylic acid.
I'm so glad you're not sitting right here and just like running and grubbing going down the hallway.
Yeah.
Sounds like somebody has
I
bad.
don't understand why everyone's sports teams just like meets in classrooms. Like, I don't understand. And if they do, like, why don't you check to see if the room is booked? That'd be just fantastic. But anyway, so yeah, acyl chloride with water will form a carboxylic acid, which we have here. And I don't remember what that's called, but it's a carboxylic acid. Any questions so far? Okay. So this next one, this is a carboxylic acid combined with an alcohol, acid catalyzed. That's Fischer esterification, right? So our first step, carboxylic acids are towards the right of the stability line. So we know that that electrophilicity on that carbon is lower than an acyl chloride. So, and alcohols are weak nucleophiles, so we need to protonate this electrophile to make it stronger. And we'll do that with a strong acid and water, which will give us hydronium. Lone pair of its electrons on oxygen will take that hydrogen from hydronium to break that bond. Okay, which will give us a strong electrophile, and then we also lost water right here. Okay, so now this is a strong electrophile. Now we can react with our alcohol. So oxygen has 2 lone pairs of electrons, nucleophilic. It will attack the electrophilic carbon, which will break this double bond, and those pi electrons will go to neutralize that positive charge. Okay, so I added this whole alcohol to that carbon there. This hydroxyl group had no change, and then this one, that double bond broke, and those pi electrons stayed on that, or went to that oxygen to neutralize that positive charge. Okay, so now this oxygen has a positive charge. It's too many bonds. Okay, so again, we're going to have that intermolecular hydrogen transfer. Okay, well, we'll move the hydrogen from the alcohol that we just put on there to one of those OH groups to form a good leaving group. Okay, so we have OH2 with positive charge. We know that's a very good leaving group. We know that'll come off. Okay, And now this oxygen here, 2 lone pairs of electrons. To keep that to keep that carbon tetravalent, those lone pairs of electrons will come down to form a double bond. Okay, keep the carbon tetravalent. We lost water. It's getting a little messy, I'm sorry. Okay, so to recap, this water came off here. Okay, and these lone pairs of electrons from this oxygen came down to form a carbon-oxygen double bond here. Okay. And then this group is still connected to that carbon. Okay. Everyone following me? Okay, so now that oxygen again has too many bonds, that hydrogen will come off. And that is our ester product. Okay, and remember in esters, when you have that carbon-oxygen double bond, which is bonded to an oxygen, which is bonded to whatever R group. So that is Fischer esterification, and that's our ester product. Okay. So, and then if you have, like if they'll ask you to not do the mechanism, just what's the product of this reaction, you know that this part of the alcohol will just connect here, and this OH and that H will combine to form water. So as a shorthand, if he just asks you for the product instead of the whole mechanism.
Okay, go back to that screen. I want to take a picture of it.
We good? You good to move on?
Go ahead. I can listen to your lecture and catch up.
So this is taking us way back to last PowerPoint. Remember when we did reduction of carbonyl compounds with hydride donors? Okay, so this is another example of that we didn't go over in the last PowerPoint. So this is an amide. An amide is when you have that carbon-oxygen double bond connected to nitrogen. So if we react it with a hydride donor, lithium aluminum hydride here, okay, and remember when you do the reduction with lithium aluminum hydride, you have to work up because you're working with metals. Okay, so remember, pretty much anytime you're working with metals, inorganic, you'll have to work up to get rid of those metal ions. And you'll end up with an amine. Okay, so here's mechanism for that. Remember this aluminum hydrogen bond, that's where our electrons are going to come from. This is the nucleophile. Okay, and here's our hydride. So that aluminum hydrogen bond will attack the electrophilic carbon, break the double bond. Okay, we'll add the hydride here. Okay, and remember with the aluminum hydride, that whole thing will connect to that oxygen up here. Okay, because oxygen has a pretty good affinity with aluminum. So those will bond together. Okay, so this whole thing is a good leaving group. So these lone pairs of electrons on nitrogen will go to form a double bond here, push off this whole group here. Okay, which will give us this. Okay, and then we'll react with another molecule of the lithium aluminum hydride. Okay, which will, again, arrow comes from the aluminum hydrogen bond, attacks the carbon here, which will break this double bond, and then nitrogen has a positive charge, right, because it's too many bonds. So that will break that carbon-nitrogen double bond, and then it'll neutralize the positive charge up here and give you an amine, okay? So the net reaction, we add 2 hydrides to that carbon here and give us this amine. Follow me? Okay. Here's an example of that. These aren't too bad, pretty simple. Okay, so react with lithium, aluminum, and remember you need to use a organic solvent with aluminum hydride, so like THF and diethyl ether are really the only 2 you can use. Okay.
Would you be more prone to give you THF over diethyl ether? Or 50-50?
Probably 50-50, honestly. But I think those are the only 2 he'll give you. So again, air comes from that aluminum hydride bond, which will attack the carbon, electrophilic carbon, break this double bond here. Those electrons will go to that oxygen. Okay, and that whole thing connects to that oxygen up here. And the aluminum holds a negative charge there. Okay, so we added 1 hydrogen there. And now this nitrogen has a lone pair of electrons on it. It's going to come down to form a double bond and push off that whole group there. And again, from like the last PowerPoint, don't worry about where those oxygen and aluminums go. They come off eventually in the workup, right? So, but you just don't have to worry about like in the mechanism writing down where they end up, because they do eventually get washed off. So now we formed a carbon-nitrogen double bond here. Now that nitrogen has a positive charge. Okay, we're going to react with another molecule of aluminum hydride. Okay, again, it'll attack that carbon here, break the double bond, neutralize that positive charge up there. Okay, which adds another hydrogen to that carbon here, making it CH2. And then we just have that NH2 single bond now. Here's our amine. Okay, almost done. So last thing in that PowerPoint is just reactions of carbonyl compounds with carbon nucleophiles, which aren't anything too difficult or anything you haven't really seen before. So the carbon nucleophiles we know so far are Grignard reagents and cyanide, and then we just started enolates, but we'll get to enolates later.
I know on the homework we did Gila,
Grignard reagents.
no, there's one for Gilmar.
It was very odd. I had to like follow the book to like find the mechanism because it wasn't
Gilman.
in his notes.
Gilman reagent.
Yeah, I don't know what that is.
Well, it was a reaction with BRCULI or something, right?
Yeah, it was odd.
Yeah, it wasn't Grignard.
Yeah, I'm not sure. I mean, I'm sure it's
I had to Google
similar.
it to learn a little bit about it. 'Cause
Yeah.
don't
Yeah,
do
I had
it.
to do the same thing. I had to like follow it straight out of the book. I
Yeah.
looked through his PowerPoint. I'm like, there's nothing in here on.
Well, he definitely won't test you on that because he doesn't go over in
Homework's not
class.
till Friday, right? Not,
Yeah, it's due Friday.
that's good, because I have to work.
Mhm. But yeah, he definitely won't test you that, but I'm assuming it's similar to Grignard reagents. It's probably just another carbon nucleophile that you react with metals and all that. So anyway, so carbonyl compounds are electrophilic, right? Cyanide is a strong nucleophile. The electrophilic or the nucleophilic center is on this carbon because that's the active electron pair. Okay, so that electron pair will attack electrophilic carbon, break the double bond here. Okay, we'll form a carbon-carbon bond here, add cyanide to that carbon. Okay, and I'll make an oxygen anion up here. Okay, and then we can just protonate this from strong acid aqueous solution. And we'll end up with this. Okay, so this is an addition, nucleophilic addition reaction and not substitution because we're not taking anything off. So our net reaction, we just added this cyanide to this carbon here and protonated that oxygen here to form an OH group, and we added cyanide. So reaction of carbonyl compounds with a Grignard reagent. So you remember Grignard reagents, we react a bromoalkane with magnesium, and that will insert a magnesium atom in between the carbon and the bromine. Okay. Magnesium will be positively charged, which will make carbon negatively charged, okay, which makes this a carbon nucleophile. Okay, and the electrons come from the carbon-magnesium bond. So electrons will come from that bond to the electrophilic carbon, break the double bond again. Okay, so here, similarly to the aluminum, that whole thing will attach to that oxygen up here. Okay, so then we work up, again, anytime you use metals, really, you have to work up to wash off those metals. So that'll wash off this magnesium and then protonate that oxygen here. Okay, and this forms an alcohol. Okay, as if you didn't need to learn another method on how to make alcohols. So you have at least at least like 20 right now. So
I hated that so much, Lydia. So much.
okay. So last example, and then we'll be done. Okay, so this is a ketone, right? And a Grignard reagent. So again, the electrons come from that carbon-magnesium bond. So why did I go over? Oops. Okay, we'll attack the electrophilic carbon, break that double bond. Okay, so remember the magnesium bromide will attach to that oxygen up there. Okay, and that ethyl group will attach to that carbon there. Okay, so now we just work up to get rid of those metals and protonate that oxygen up there. So I'd probably put this back in line structure just to make it a little less confusing. So 1, 2, 3, 4, 5. So this would be our alcohol. Okay.
One second. Thank you.
Okay. Any questions? If not, that is all I have. And the website I showed you a few weeks ago, I don't know, they might have something on nucleophilic acyl substitution. It's called ChemTube 3D if you want to go look at it. I'm not sure if they have.
What is it?
ChemTube 3D. I sent it to you guys a while back.
What I've been using lately is Khan Academy.
Yeah, Khan Academy too. That was very helpful. We'll have explanation videos for a lot of this stuff.
Yeah, so my problem is figuring out, like, where you're going up there, he shows how it goes from left to right.